All right. I guess it's time to start. We have a large amount of people here. So welcome, everyone. I'm Luca Rovige. I will be your lecturer for this Physics 1B update session. So the lecture will be 12:30 to 1:45 p.m. every day, Monday to Friday. Online, the Zoom link will be always the same. So yeah, you can keep this Zoom link. Otherwise, you can access the Zoom link to BRINLearn with the right session that are timed. My office hour will be 2 to 3 p.m. Monday and Thursday. This might change depending on the schedule and if it fits with people and if it fits with my lecture schedule and TA office hours. But for now, it will be this timing, and I guess I will keep the same. You can join the same Zoom link as the lectures. I will leave it active for the office hours. And as it has been globally requested by a lot of people, all the lectures will be recorded and uploaded to BRINLearn daily. Though note that it might take some time to upload because I'm gonna upload them to the cloud and it's done automatically by Zoom, but it should take like somewhere around the lecture time to twice the lecture time to be available, but could be up to 24 hours after the lecture to be available. So yeah, be mindful of that. And if after some time it's not available, and let me know. I'll see what I can do. Maybe upload my own recording or something like that. But that's how it's gonna go. Also, if at any point you have questions, don't hesitate to ask. I don't know how exactly it's gonna go with this Zoom session, so for now, do as it feels more natural to you. Just you can ask in the chat or raise your hand or just speak. We'll see if something is better at some point. But for now, just feel free to ask your questions and I'll answer them. Okay, so for the discussion sessions, your TA name is here. I realize I haven't put the email address in this slide, so it's on the syllabus that is accessible on BRINLearn, so you can find it there. Otherwise, I'm sure you can find it somewhere else. So the discussion sections hours will be Monday and Wednesday, 11 to 11:50. And in this discussion, the TA will go through relevant topics and problems, maybe do a quick refresher on the courses, the lectures that will be relevant for the day, the problems of the day. For this discussion, attendance is optional, though I'm not sure yet if the TA will be recording this discussion section. So yeah, I'm not sure of that yet. But anyway, you'll have to submit your discussion section sheets, worksheets, and they will count for 10% of your final grade. You need to upload them on Gradescope no later than Friday, 10 a.m. of each week. And obviously, if you've been to the discussion section, so Constance, when will this sheet be available? I believe, I mean, that's again something that your TA will set. I'm not sure, but I would guess they will be made available at the beginning of the session of the daily discussion section. And then you can have access to them and either where is the Zoom link for this discussion section? I'm not sure. I will ask the TA to set that up and either make an announcement or give me an announcement to make so you can access them. I'll try to do that today, so the Zoom link is ready before Wednesday's discussion section. So we will be using Gradescope for discussion section grading and submitting, and also for the final. So you should be automatically enrolled in the Gradescope, but if you're not, you can write or take a picture of this course ID and the password and register manually. All right. So let's go over the fun stuff. So there will be only one final exam, accounting for 40% of your total grade. This final will be Friday, August 2nd from 10 a.m. to 1 p.m. And since the whole class is done remotely, the final will also be done remotely, but will have to be done during the scheduled time, 10 a.m. to 1 p.m. So yeah, you'll have to be available for these hours. Okay. For homework now, so I will assign textbook problem every week on mastering physics for the material for the week's worth. For the material pertaining the week's lectures. These homework will count toward your final grades for 10%, and set 4 tries per questions for these each question of the homework. And you can try 4 times without having any penalty on your homework, but past these 4 tries, you will lose some points on the question, because just don't want you to try any random combination of the tries to get the answer right. Just think about it. And after discussing with the TA, I think the policy for the homework will be that they will all be due by the Friday 10 a.m. of the last week, so basically before the final. But that doesn't mean you should wait the last time to do every homework, and I will provide suggested dates for each assignment. Basically, there will be 1 or 2 every week, and I strongly advise you to do them in that time frame. That will help you being ready for the quizzes, not fall behind, because if you have to do 8 set of homeworks that each take more than an hour in the last week, while you have to work for your final, it's going to be very complicated. And of course, if you work on problem for your homeworks, then you might find something similar in the weekly quizzes, and that's obviously going to help with your understanding of the class. So strongly advise you to do them in like regular time frame, but with this whole remote lectures, it's not. I want to give you the freedom of managing your schedule as you want, and as you can with other time constraint you might have. So for counting toward your final grade in a significant manner, I will be organizing weekly quizzes that will be on during class time. So okay. Before the quizzes, Melanie is asking if I be giving a link or the code for Mastering Physics account. Yes, I will. Yeah, I guess I forgot to include, but yeah, I can give you that. Otherwise, I think you can access it directly through BreenLearn. There might be a link, but yeah, I think it's on the, I believe the code is on the syllabus I put online on BreenLearn. I will check that, and if it's not, I will provide it in an announcement or in another manner. And for the homeworks, yeah, you can work together for the homework anyway. I don't have, it's not like I could enforce you not doing it. So yeah, thank you, Skylar. That's exactly the way to access the courseware. Thank you. And yeah, for the homework, you can work together, try to still have your own answers and work but yeah, I believe community work can be useful to grasp the concept. So you're welcome to work on the homeworks together. All right, any more questions on the homework and this material before I pass to the quizzes? All right. So as I was saying, weekly quizzes. So one every week, excluding this first week because we don't have course material to be quizzed over. So no quiz this week. First quiz will be next Tuesday, I guess Tuesday of next week. And so there will be a total of 5 quizzes. There will be a quiz the week of the final. And so the average of the quizzes will count for 40% of your total grade. So it's really important that you work toward these quizzes. There will be, if you went through the last week worth of material, if you work through it, you should be doing good, doing great at these quizzes. There won't be a way to try to make very difficult problems, more like assessing your understanding of the lectures and making sure you grasp the main concepts. So for these quizzes, they will be available on Gradescope starting at the beginning of the allotted time, and you'll have to submit your answer sheets before the end of that allotted time. So there will be 40 minutes. I will try to, for the quizzes to be roughly 30 minutes in work equivalent time. So you have time to download the sheet and then, take a picture or upload your answer sheets. And so you're not rushed to do that and you have time to figure that out. So I'll try to keep the material for the quiz less than 40 minutes. So you're not stressed about doing those manipulations. And another important point about those quizzes is that your lowest quiz score will be dropped. So let's say you've attended 5 of the whole 5 quizzes and you have one low grade, or I guess your lowest grade of those 5 quizzes will be dropped. But for some reason, let's say you couldn't make it to one of the quizzes, then you will have 0 point toward this quiz, but I will drop that one. So that means you can miss one with no penalty. So if you have something you need to be doing during a quiz, you can miss one and you won't be penalized, beside the fact that you won't have another joker and not another free pass for a quiz. Because I won't be making any makeup quizzes. So all the lectures you're free to follow them at different time. They will be recorded. So I don't ask attendance for the lectures. All I ask every week is 40 minutes of your time where you're here for the quiz. And then the rest of the time you can make up your time, your agenda as you wish, but I do require those 40 minutes of your time every week. Any question, quizzes? All right. So that leaves us with my grading policy. So as a summary of what I said, discussion counting toward 10%, quizzes 40%, the final 40%, and the homework is 10%. I will use a classic absolute scale, that won't curve. And if you have, basically, if you have an absolute score higher than 90%, you will receive an A. And I won't be doing makeup final on regrades, except for emergency situation that will need to be approved beforehand. All right, for the textbook for this class, I'll be basing my course on University Physics with Modern Physics by Young and Friedman. And I strongly encourage you to follow, to use the textbook to get additional details and context to my lectures, especially from the relevant chapters. I will point for every chapter of the lecture of the course, I will point towards the relevant textbook chapters, because this lecture, I mean, this course will be 6 weeks with 1 lecture every day. So it's going to be definitely fast-paced. I won't be able to go over everything in extremely fine detail. So you might be able to find more explanation or derivation in the textbook. So it can be useful. And also, I guess the derivation I will make will be of a slide. So it's not always the best to follow slide derivations and stuff like that. So it would be useful for you to follow the textbook, though I will plan my course and my lectures to be self-sufficient, meaning that I won't ask you something that's in the textbook that's not in my lectures. So yeah, good. So yeah, it's a good additional context provider, but it's fine to just attend the lectures and go to the discussion section. Also really important, you were all automatically enrolled in the inclusive access of the textbook, which means that the cost of the electronic version of the book and Mastering Physics will be charged automatically to your Brin bill. So if you want to opt out, you must do so by this Friday, so the Friday of the first week. So, but that means you will lose access to the textbook and Mastering Physics 2. And we will be requiring Mastering Physics to do the homework. So it's definitely not advised to do that. And if you have any question about Pearson and the inclusive access, you can contact Simona Grace here. Here's the email address. Before I switch to the skill, any question on the textbook and inclusive access? All right. So this is going to be, I mean, this is an estimate of the schedule for this course. So 6 weeks, first week. So this week is going to be mainly centered about fluid and periodic motion. So book chapter 12 and 14. And then we'll switch to mechanical wave and the applications to sound. And this will be kind of the first part of the lectures on fluids, wave, and periodic motion. And starting with 3, we will start the electromagnetics, electricity part of the lectures. So starting with charge, electric charge, and electric fields. Yeah. Let me finish with the schedule and I'll answer your question, Jaden. So electric field, Gauss law, electric potential, and we'll use those concepts to learn about capacitor, dielectrics, current and resistance, and apply those to direct current circuits. So you see that the final week, the week 6, mean, we'll have the final the Friday, so I don't want to be, still teaching some materials the day before the final. So the idea is maybe to have some last concepts during the lectures, maybe Monday, Tuesday, and hopefully Wednesday, Thursday, just have this time to just go over some review, make some practice problems. You will be able to ask me some question about the whole course. So yeah, that way we have some time to prepare the final. Okay, so for the quizzes, so the question is, are we supposed to be on Zoom during the quizzes? So I will say no, though I will start the Zoom. I will be on the Zoom. So that way, if you have any questions or if you realize something is wrong with one of the questions, you have technical issues, you can contact me, ask your question directly. But otherwise, you can do the quiz. You can do the quiz without being on the Zoom. Though I encourage it, because if something comes up during the quiz, somebody brings something, an issue, a question, and you're on the Zoom, then you have the direct information. So, but otherwise, you can just join the Zoom when we start the lectures. Yeah, we can about your specific issue about having more time for the lectures. We can chat. Can see the detail by email, but yeah, I think we can find a solution for that. Maybe you can just get the quiz during the whole lecture time, and then you follow the lecture that with the recording. But yeah, send me an email and we'll see the details by then. And that makes this question makes a good segue. So if you need any accommodation, you should contact the Center of Accessible Education. You can send them an email or call them and explain them your situation. There's also resources that can help you for if you need support on learning, and you can contact them using the numbers, and all these resources will be available on the syllabus in a more detailed way, so you can read through them. Also, I got a message from your peer learning facilitator. So the peer learning facilitator is I guess a fellow student that will organize session for academic advancement program students designed to provide support for first generation low income students who have been historically unrepresented in education. So everybody is welcome to apply to AAP, and there's the website and some links. I will also put this as an announcement in the chat. And if you're interested, you can send an email to Smera, which is your PLF for this course. And if you're facing any gender discrimination, there's also resources you can access and some contact you should be aware of. And otherwise, if you have any issue during this class and during this course, I know you're not on campus per se, but it also can mean that you don't have your usual social circles that can provide you support. So you're free to contact me if you have any issue pertaining the course or anything around that. And we can try to find you some support around the university resources. And there's a message of the Dean of Students that I can summarize by: don't cheat, it's not worth it, and it won't help you getting far and understanding concepts. So just be honest and everything's gonna be fine. All right. Any questions pertaining the syllabus? Otherwise, if something else come up, you can send me an email. I think, yeah, I mean, I will be doing also office hours from 2 to 3 today, even though it's the first day. All right, my email, it's on the first slide. So basically it's, yeah, be careful. This is an L, like as in Lucas, not an I. People often mistake this for an I. So, and the slides, I will upload them after every lectures on BrainLearn. I think it will be one of the, I don't remember exactly which menu, but right now there's the these intro slide already there. So basically I upload the rest of the lectures as we go after I've showed the slides. So you will be able to find them. Oh, they are? Okay. I will look into it. Maybe I've set the wrong date or something. Yeah, thank you for bringing that up. I will look into it. All right. I guess after the lectures, I will try to solve this issue, and and also upload the first batch of lecture slides. So if by tomorrow it's still not available, you can either bring the issue at the beginning of the lectures tomorrow, or just send me an email and I'll try to figure that out. All right. Let's switch to the actual lecture now. All right. So, oh, I lost the chat. Okay. So during the first part of this course, probably in the next 3 days, we're gonna be talking about fluids, fluid statics and fluid dynamics. So this corresponds to chapter 12 in Young and Friedman, so in your textbook. And so let's start. Oh, and also, you might have noticed, but I'm not a native English speaker, so if at any point something is not clear just by the way I've said it, don't hesitate to ask again to for me to re-say something. There's no, I won't take it personally. So let's get started. So why do we care about fluids? I mean, one of the fluids are all around us. We're existing in a fluid. The air around us is a fluid. And even inside our body, which is mainly made of water, fluid dynamics is a massive part of our physiology and how our body works. So it's really important for us to understand how fluids behave, just to understand the world around us and our own bodies. Beside that, fluid dynamics explain how we're able to make a plane fly, or how we're able to launch rockets. So there's really a lot of things that are driven by fluid dynamics. So it's really an important domain of physics. But what exactly is a fluid? Yeah, it's important to define what it is before starting to study its behavior. So a fluid is a collection of molecules or atoms that are arranged randomly, but still held with cohesive forces. But these forces are relatively weak, which means that this fluid will not resist deformation. It will have only a slight resistance, and that means that the fluid will be able to flow, meaning, for instance, taking the shape of the container you put them in. So, for instance, if you put an ice cube, so an ice cube is solid. If you put it into a glass, it will keep its square shape. But if you put just liquid water into your glass, it will just take the shape of your glass, of the glass you put it in. So that's an easy way to know if something is a fluid. Is it taking the shape of the container I put it in? And from the three typical state of matters we know, we typically consider, so solid, liquid, and gas. Obviously, liquids are fluids because in common language, we sometimes even use the two words indistinguishably. But also gas are fluids because, yeah, if you put them into a container, they're just gonna expand, take the whole space and take the shape of the container. So these are fluids. And since fluids are a bit more diffuse than solids, it's not always easy to characterize them with just a mass or volume because those can change relatively quickly, depending on what you're considering. So that's why we want to define a quantity that's more adapted to these fluids. And one of these quantities is density, because density measure the mass of substance for a given volume. So if we define the density rho here, then it's equal to the mass divided by the volume of the fluid you're considering. And the density is expressed in kilogram per cubic meters. And so, yeah, if you take more, if you add more water to your glass, you will have a larger mass and a larger volume overall. But the actual density of the water of the material stays the same. So that's an interesting parameter to consider to characterize more consistently your fluid. And if we consider this density, we can see that there's very strong differences between air and water, and usually more generally between gases and liquids, because if we look at the air, which is a gas mainly composed of nitrogen and oxygen, we see that density is of the order of 1 kilogram per cubic meter. And if we now consider water, which is a liquid, we see that the density is almost 1,000 times more higher than the air. And this difference in densities, difference in very important characteristic of the fluid, will cause difference in behavior, in pressure, interaction with solids, with buoyancy, and also in propagation of waves, light waves or sound waves. So it's a really important parameter for fluids. Okay. Okay, so another important parameter to consider when looking at fluid dynamics and fluid statics is the pressure. So the pressure is the force per unit area. So it's expressed, its unit is the Pascal, which corresponds to Newton. So Newton is the force divided by square meter, which is the surface. So here we can define a general expression for the pressure, the force divided by the area. And it's in order to kind of understand the difference between the force and the pressure, we can look at the difference of pressure under the feet of an elephant and under high heels worn by a person. So obviously an elephant is much heavier. It's going to be thousands of pounds, but its feet are also much larger. And so that leaves us with a typical pressure under an elephant's feet of the order of 75 psi. But now, if we consider a much lighter person on high heels that are extremely thin, we see that the pressure is more than 1,000 psi. And so even though the pressure is, even though the force is much stronger for the elephant, the pressure is much larger with the high heels because of the small area it's pushing on. So do you need to know the conversion? No. As a matter of, I myself don't even know those conversions. I would say it's remember that 1 atmosphere is 10 to the 5 pascals, because that's just very useful to know. It's kind of common knowledge, and but otherwise I would say, yeah, if at some point you need this kind of conversion, it will be given to you in a problem. So do not worry about learning random conversion between a lot of weird units. Okay. And yeah, when we are talking about pressure, something you might hear a lot, or just hearing, when commonly talking about pressure, is the atmospheric pressure. That is basically the pressure that we experience when being on the ground, and this pressure is the pressure that is due to the whole atmosphere. So the 20 miles of atmosphere of air pushing down on us, because this atmosphere has a way, and the pressure we're experiencing, the atmospheric pressure is just this large column of atmosphere of air pushing down on us. And that atmospheric pressure typically 10 to the 5 pascals, that corresponds just to 1 atmosphere. And something that you need to realize with pressure is that it's a scalar quantity. It doesn't have any specific direction. So it's just a measure of how local fluids are pushing against all their neighbors. It's not something that has a direction. And let's say we use this kind of device, just something with a string and the atmospheric pressure inside, and you put it into some fluid. Then you can kind of measure the pressure by measuring the force that is applied to this spring. And if we put this imaginary measuring system into a fluid, we see that if we flip the spring in any direction, the spring will still be pushed because the pressure doesn't have a direction. Though what you have to understand is that even though the pressure doesn't have any direction, the force associated with this pressure have one, and it's the normal to the surface it's pushing on. So here, for instance, if we're considering this spring, we see that it's slightly tilted, and so the pressure of the fluid onto the spring is just the local pressure at this position, multiplied by the area and oriented with this normal of the area. All right. And so we've seen with the atmosphere that the atmospheric pressure that is pushing down on us is associated with the weight of this column of atmosphere. So we can try to get that more formally and understand how it works. So if we consider this fluid element here, so just a square of area A, it has, I guess, a rectangle of area A up and down and a height H. This fluid element is pushing down on what would be below it. And so it creates a pressure at this position just below the fluid element. And so the pressure below this fluid element would be the force it exerts divided by the area A, and the force of this fluid element just its gravitational force. So its mass multiplied by J, the gravitational acceleration, and divided by A. All right, and so now we can express the mass as a function of the density and the volume, because this will give us something that is more general, because the mass is very specific to this fluid element, but density is more general. So we can express with the density, rho, and the volume of this element. And this volume can be just obtained. So it's a rectangular element. So we can have the surface A and multiply by the height H. And this gives you the volume, and multiply by the density gives you the mass. And now we can use this expression for the mass and just insert it into the pressure formula. And if we do that, we see that the area simplifies, and we just obtain the pressure equal to rho G H. And this is very interesting because we started from a specific element that has an area, and now we see that this area simplified. And so this is more general and applies to any shape, any form, any size of fluid element. And we see that the hydrostatic pressure created by this element mostly depends on only depends on its density and the depth of this element, the height. Okay, so yeah, how do we get the force equal m multiplied by the gravitational force? So yes. Up. Okay. Okay. So we have this fluid element, and so it has a way, right? This fluid element has a, I guess it's not the best. Yeah, it has a way because, yeah, it's matter. And so if it has a way, gravity is acting on it. And so you have a gravity force, Fg, which is equal to minus, I guess. In that case, it's going down. So we oriented this to be oriented toward the bottom, so in the direction of gravity. And so the gravity is just the mass multiplied by the gravity acceleration. So what we're saying is that, yeah, the only force this fluid is applying on this point is just the gravitational force. And so that's how we get this F, the force equal M multiplied by J. Is that clear? Okay. Yeah. Why is yeah, good question. So, uh, oh, okay. So why here A is a vector, and so basically, so a force will have an amplitude and a direction, and so here to know the direction of the force associated with pressure, we know that it's going to be normal to the surface. So here the surface is a vector because it's just the amplitude of the amplitude of this vector is just the surface area, and then the uh, the direction of the vector is just the of uh, normal to this surface area. So here. And here we just getting I guess, the scalar version of it, which means we just considering the amplitudes of the force and the amplitude of the area. So just the surface area. Any more questions on this? So yes, yeah, that's right. In in that equation, I'm assuming that the force is perpendicular to the area, which is the case because we considering a square element that is, oriented with a flat surface at the bottom. So this square surface is actually uh, perpendicular to the gravity. And then what's interesting is see that since these amplitude and this area simplifies, it can actually be generalized to more complex shapes. So yeah, I mean the how we get the mass. No, I guess you might be confused uh because for the mass because it's not the mass equal the pressure multiplied by the volume, but the mass equal the density rho. So this is a rho, the Greek letter rho, not a P. And it just comes from the definition of the density. Density is the mass divided by the volume. So it gives us a mass equal uh, density multiplied by the volume. And yeah, and how do we get P equal rho G H? Just plugging this expression for the mass, which is the density multiplied by the volume, and the volume expressed by the area multiplied by the height. We plug that into this expression here, replace the m by rho AH, and simplify the A, that just cancels out, and it just leaves us with rho HG or rho GH. Is that clear? Cool. Okay. But the thing is, for now, we've considered like one fluid element on its own. But the thing is, uh, things don't exist on their own. They exist surrounded by other things. And so these fluid elements, this is the same fluid element we were considering before, is probably have another fluid on top of it. A good analogy to that, if let's say you're trying to get pressure in the ocean, uh, the ocean has something over it's the air, the atmosphere, and this atmosphere also exerting a force on it. And when you're doing your calculation, if you don't want to go back always all the way back to space and integrate all the pressures down to your elements, you're gonna have to set a reference point where you say you know your pressure and you're gonna use that as a base of reference. So that's what we do here. So considering we have another fluid on top of our fluid element, and this fluid is exerting a pressure, a reference pressure, P0, on our fluid element here. And for instance, that would be saying that, yeah, if you consider the pressure into the ocean, you say that the base pressure at the beginning, at the top, at the surface of the water is going to be the atmospheric pressure, and we know what is the atmospheric pressure. And so these pressures is added to the expression we derived before. So this gives us the absolute pressure at a point P in the element fluid we considered here. So it's rho GH, which is the hydrostatic pressure because of the way of this fluid element of the here. And so if we look at the pressure below it, that's rho GH, the way of this fluid element plus the reference pressure that is on top of this fluid element. That is typically the atmospheric pressure, so 1 atmosphere. And so to define things, so this total pressure, so the rho GH plus the reference pressure P0 is called the absolute pressure. And the delta P is the gauge pressure. So it is the difference to the reference point you're considering. So in our case, this gauge pressure is going to be rho GH. And yeah, an example of the difference between gauge pressure, absolute pressure would be, let's say you have a flat on your car tire. And all the air is being let out, so you have a flat. If you measure it with a gauge, you're gonna try to put some new air in it. When you measure the pressure in it, you're gonna see 0. Does that mean you have you have a total vacuum in your tire? No, it just means you have the same pressure as the outside pressure. So this would be the gauge pressure, so the relative to the atmospheric pressure. So if you have a 0 gauge pressure, it means you have the same amount of air, same pressure of air in your tire than outside. So there's no force holding it together. And if you add more air, then you're adding more pressure. But yeah, you always have 1 atmosphere in your tire, even if it's flat. Okay, let's see an example of this hydrostatic pressure calculation to get a more practical idea of what it means. So let's just consider the ocean. So what is the absolute hydrostatic pressure in the ocean at a depth of 10 meters? And what is the gauge pressure? So I guess I'm gonna just leave you 30 seconds to think about it. What you would do, you can scribble on a piece of paper, and then we'll see how it goes. But yeah, I'm letting you just a few seconds to think about it before we go over the answer. Okay. So what is the absolute hydrostatic pressure at 10 meters in the ocean? So we're using this expression. So the pressure is equal to the rho GH, which is the way of water, the way of the water that is on top of the point we're considering, and plus the air pressure that's also pushing down on the ocean. So P0, 1 atmosphere. So rho, it's 1025 kilometer per cubic meter. G is the gravity acceleration, 9.8 Newton per kilogram. And H, so this was a given of the problem, it's 10 meters. And P0 is 1 atmosphere, so 10 to the 5 pascals. So that leaves us with a total absolute pressure, which is 2 atmospheres. All right, and so this is the total pressure. And so now if we want to get the gauge pressure, we just take rho GH, so it's just the way of the fluid column, and so that means that we take total pressure and we remove just the air pressure, 1 atmosphere. So that gives us the total gauge pressure being 1 atmosphere. So this is an interesting result you can remember for, I guess, your general culture, or just making sure your answers are right, because it's pretty simple result that every 10 meters of water roughly increases the pressure by 1 atmosphere. So when you calculate an hydrostatic pressure, I would say it will be precise which one you should do. And let's say that if it's not precise, if it's not, let's say somebody has forgotten to give it, to give the detail of what pressure you should give, just, get one of the two and just precise that this is the gauge pressure, or this is the gauge pressure, or the absolute pressure. And that way you show that, yeah, you know there's a difference, and you thought about which one it was. So yeah, but usually it would be precise in the question. All right. And so now that we have this kind of basic law, we can think about the more impressive results. So what is the absolute hydrostatic pressure at the bottom of the deepest part of the ocean, the Mariana Trench? So the Mariana Trench at a depth of 11 kilometers, it's extremely deep. And so if we look at, if you use just the previous results, we've seen that 10 meters of water correspond to 1 atmosphere. We can get a pretty quick and straightforward answer. The pressure is just going to be the depth, the total depth divided by 10 meters, and plus the 1 that is the air pressure, the P0 pressure of the atmosphere. And so if we do that, we obtain a total pressure at the bottom of the Mariana Trench that is 1101 atmosphere. So this is a crazy amount of pressure. It's more than 1,000 times what our body are made to sustain. And so that explains why submarines, like deep ocean submarines, have to be extremely well engineered with specific materials. Otherwise, they would just not resist this kind of pressure. And that's why the deepest part of the oceans are less known from the humanity than even some part of space, because it's just so hard to reach those points with anything we can make. Okay, here's another small lecture questions, and it will be the occasion for me to launch a new feature. Is all along my lectures, I will have those multi-choice questions for you. Just quick concept test to see if you're, if you got the concept, and I will try to do a Zoom poll. So I think, are you seeing the Zoom poll right now? You can answer. Yeah, I see some people are answering. So you see there's more answers on the poll than choices on this slide. It's because some of my question will have up to 7 answers during this course. So just using one poll that will refresh. So yeah, answer, thinking about it, give it some thought. It's not, you don't have to make a calculation. It's just more like basic understanding on a hunch, and then we'll see together what's the real answer and why. Yeah. All right. I got, okay, giving you 10 more seconds, and then we'll go over the answer. Yeah, okay. I mean, it's working well. Everybody's participating. That's nice. And yeah, okay. Okay, I've ended the poll, and you've answered almost with the absolute majority, 49%, the correct answer, the choice 5. Choice 3 was a strong contender too, and yeah, we'll see why it's not the right answer. All right, so yeah, the correct answer is number 5, and that is because, yeah, we've seen that in a hydrostatic equilibrium, we've seen that the pressure here expressed P equal P0 plus rho JH only depends on the height of the fluid. So here they all have same surface at the bottom and the same height, so the pressure is gonna be the same on this bottom thing. I see that a lot of people, I mean, a decent amount of people answered the choice 3, which I agree makes sense. Like, we have more water, so we have more force. Why is the pressure not stronger? That's a valid questioning. And the reason for that is that the extra force that is present in this case is actually pushing against the angle walls. So because we see the pressure against the wall here, it has some component in the direction of gravity. So yeah, the fluid is pushing against the wall, and so that's why some force is lost here. And on another hand here, in the case A, some force is going upward, it's pushing against the wall, which makes the pressure the same amount of the rest of the cases, even though there's less water here. So this really is a good example of the pressure below a fluid column really depends on the height and not the shape. That's something you have to remember. Yeah, just consider the height, and it's gonna give you the pressure, the hydrostatic pressure. So question, what concept were you teaching when you explained how needles and knife worked? was mostly about explaining the difference between force and pressure, because it was more like if you put a force on a smaller surface, smaller area, then you get a high pressure, not because the force is strong, but because the area you exert your force is pretty small. You really concentrate your force on a small zone, which make it high pressure. So that was what I wanted to convey with this analogy. All right. All right. Okay, we'll continue doing those poll quiz during the lectures. It's because it keeps you you know, keeps you awake and following the course, and it's more. Okay, so here's a new poll. So now let's consider this situation. Okay. So we have this tank of water that is open to the atmosphere at the top. And we have pipes coming from this water tank, going down a hill and slightly up to a faucet here. So given the apparent length we have here, what pressure, how would you calculate pressure at the end of the faucet here, given this situation? Okay. All right, 10 more seconds. All right, and that's it. All right. Okay, we have a strong majority of people voting for question 5, answer 5, which is basically saying that the pressure is determined by AC minus E. And that is the correct answer, because again, the pressure in the fluid in a continuous single fluid depends only on the height. And so, yeah, all these distances, B, oh, my bad, B and D and F doesn't correspond to any height variation. So, yeah, it just depends on the height of A, C, and E. And a valid question you could have is, but that's weird because there's no really, we look at this here, the fluid here, there's no really water above it that would be pushing it. And that's correct. Most, I mean, there's no like physically water above it, but this water here have a way and it's putting some pressure here. You want to go lower. Basically, this water want to go lower by the gravity force. And so it's pushing along the pipe and continue pushing. And this force here is retrieved here. I mean, this pressure, and that is retrieved here. And so that's why you have still a pressure here, even though there's no actual water in this area here over the fluid. And that's how, at least in more, I don't know, in the cities, but that's how the pressure system for your house water works in more, at least in more rural area, where the water tank, fresh water tank, will be placed on a hill, and just gravity will be supplying the pressure force to get some water pressure at your house. And that works even if you're on the second or third floor of your house or your apartment building, just because, yeah, the initial tank is still higher than that. Okay, let's see. Okay, new, uh, okay, new questions. Gonna leave you a little bit less time for this one because I want to go over a few things before the end of the lecture. We have this U-tube filled with mercury, which is a liquid. And so in this situation one, we have those two part of the U-tube. One has a larger area here, the second one has a smaller area here, and we put some water in the second part, pushing some of the mercury up, but the higher part of the water is still at the top here. What's the relation between the pressure at point A and point B? Oh, yeah, sorry, I realized I missed some questions about the previous one. So I'll come back after I give the answer about this one. All right, that's it for this poll. So I have a majority of choice 3. So saying that the pressure at PA is smaller than pressure at PB. And that is correct, because the concept that the pressure at the same height is the same is valid only when you're considering a single continuous fluid, but not when you have two different fluids with a disparity and a discontinuity. Indeed, an easy way to realize this is if you consider the pressure at point A, it's at the interface with the air. So the pressure is just the atmospheric pressure P0. And it would be the same at the top of the water here. Here at the interface, we have P0. And so if we go down a little bit, we have the way of this column of water that adding to the pressure, leading to a difference in pressure and higher pressure, point B. Okay. And okay, going back real quick to this. So yeah, basically there's the pressure will be given by the shortest the distance height between the 2 points, but yeah, there's a negative change. So actually the gravity doesn't the gravity between the force between those 2 points is just depends on the difference of height between the top here and the bottom here. But yeah, I know it's almost it's kind of the end, but the last, this slide I want to show kind of explain this more formally. So because it shows how to get the difference in pressure between two, let's say, random points in a uniform point. Some 2 points at a different height, not the absolute pressure, but just the difference in pressure between 2 points. So we have the first point, the pressure P1, that is at a height H1, and the pressure H2, the pressure P2 at a height H2. And so if we want to get difference in those two pressure, so the pressure is rho GH1 plus P0 and rho GH2 plus P0 for the second point. So if we get the difference in pressure between the two, the P0 simplifies. P0 simplifies, and we get delta P equal rho GH, rho G multiplied by the difference in height, H2 minus H1. And so if we apply this to the water tank situation, we see that just we take the H1 here, the H2 here, and we see that the difference in pressure between those 2 points are just linked to difference in height between the 2 points. So yeah, you could go down by 1,000 kilometers and up with those concepts. I mean, we could consider more complicated physics like frictions and stuff like that, so that would impact the pressure. But in this framework we're considering of non-viscous fluids, yeah, the pressure only depends on the height. And yeah, I see a question on this concept test. So does difference between the densities affect the pressure? So yes, because I mean, for point A, it's pretty simple because just the atmospheric pressure. But let's say you go to some distance down, like let's say a small H2 distance here down, then the pressure at this point will be P0 plus rho water. So the density of the water, G and H. I mean, H2. And, oh, I guess, no, this is mercury. So yeah, the density of mercury, not the density of water. And if we go down here, so here we have P0, and if we go down the same height, then we would have done here, we would get rho water, GH. And so if mercury has a different density than water, then the pressure at the same depth for the same at the same depth in the same situation will be different. So what if you want to know the pressure somewhere in between the larger and the smaller tube? I mean, so let's say you want the pressure here, right? You can start from this side. So here you have P0, and then you go down here. And you have P for P0. I'm not going to write it because I'm on my pad, but rho GH plus P0. So you get the density here. Now, if you're here, there's two ways of doing it. You can go down this way, and you'll have, this is the same in continuous fluid. So the pressure between here, the point A, and let's say point C here, it's just going to be rho G and the difference in height between those 2 points. So you can do that because you're in the single fluid. Alternatively, you could start from this side, and you can get, this is P0, so you can get the density here, which would be P0 plus well, yeah, it's terrible to write with my pad. I'm sorry, but it would be basically P0 plus density of water, this height of fluid column, and then J. And so now you would have another rho, another pressure that would be, let's say, call it the P1. And you could guess the density, the pressure here using this could be your new reference pressure. and then you're now in a one single continuous fluid, and you could go down these points, and the pressure would be P1 plus the depth between those 2 points here. Is that clear? Yeah, both sides give the same results. And actually, that's why you have a different height between the two. Basically, they adjust because they have different density, and so the height adjusts. So the pressure in this part is just physically correct. Yeah, let's say if you take the pressure here, it has to be correct starting from this side. It has to be the same one as if you start from this side. Otherwise, you'll have two different pressure for the same point. And the pressure is the same here. I mean, it's one single point that is at the interface. So there's one pressure, and you can obtain it going continuously from from the water, or continuously going from the mercury. So, of course, pressure has to be the same one because it's the same pressure. So you will get the same results. And all right, that's the end of the time for our first lecture. And do you have any? There is no upward pressure. So the pressure has no direction. I've gone the wrong direction myself. So yes. Pressure has no direction. It's a scalar quantity. So pressure at a point is just defined by, in this hydrostatic equilibrium, just defined by the way of the columnar fluid that is above it. But yeah, pressure has no direction. And then and so if you take a fluid element here, the thing is, I guess. So there is a pressure here, and so this fluid is pushing against this other fluid here, but since for the Newton's third law, you have a reciprocity of force. So this fluid is also pushing on this one. So yeah, no, pressure is not has no direction, just a measurement of the local pressure at a specific point. And then depending on the area it's pushing on, where this area is, how this area is oriented, your force will have a specific direction.